The Apollo 11 Command Module 107, is one of the most iconic and important artifacts in the National Collection. The Apollo 11 mission to the Moon in July of 1969 began at the Kennedy Space Center on a Saturn V rocket. The spacecraft itself is obviously at the tip of the rocket and consists of actually three major components. There was a command module attached to a service module. The service module contained all of the power equipment and the consumables. The command module was sort of the command center, which took the three astronauts for most of the mission. Attached to it was a lunar module, a specialized spacecraft in two parts, which would take two of the three astronauts to the surface of the Moon. The bottom part, called the descent stage, would land. The ascent stage, where the astronauts lived during that part of the mission, served as both a control center and also would launch all by itself, called the ascent stage, after the exploration, and then rendezvous again with the command and service module in lunar orbit. Once all three of the astronauts were together again, the lunar module is ejected and they come home in the command module and service module. The only part to return is the command module, and that's the part that we have in the collection. That's Command Module Columbia, one of the most famous objects in the Smithsonian.
How a vehicle travels through space is different from how it travels through air. What's fascinating is that continuous propulsion is not necessary to get the spacecraft to its destination. Since there's no atmospheric drag, there are generally no other forces acting upon the spacecraft besides gravity. So we can get the spacecraft to its destination by thoughtfully exploiting gravity. The scientific study of how gravity affects spacecraft and planets in orbit is called orbital mechanics, or orbital dynamics. Our understanding of orbital mechanics dates back to work done by Johannes Kepler in the early 1600s. Working from observational data of Mars, acquired by his colleague Tycho Brahe, Kepler observed that Mars tended to speed up when it was closer to the Sun, and would slow down when it was farther away, all the while traveling on this elliptical trajectory. This led Kepler to posit three laws of orbital motion. The first states that the orbits of planets are ellipses, with the Sun at one focus. Kepler's second law states that the line joining a planet to the Sun sweeps out equal areas and equal times. This can only be true if the body, Mars in this case, is moving faster while it is closer to the body it is orbiting, which was the Sun. And Kepler's third law states that the square of the orbital period, the time it takes to complete one orbit, is directly proportional to the cube of the mean distance between the Sun and the planet. Now, Isaac Newton incorporated Kepler's laws into a universal theory of gravity as the fundamental force acting on everything in space. Even though we might think of astronauts in space as being in a weightless environment, there is no place in space that is outside the influence of gravity. Newton postulated that the force of gravity between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. So if the distance between two bodies is doubled, then the gravitational force experienced by each body will be cut by a factor of 4. It is convenient to multiply the universal gravitational constant g times the mass of whichever planet is being orbited to get a new constant, typically called mu. Here the Greek letter mu is for Earth, so mu is the product of the universal gravitational constant with the mass of Earth. Now, about the same time Kepler observed his three laws of orbital mechanics, Galileo had an insight worthy of an astronaut. By ignoring atmospheric drag, Galileo concluded that gravity alone acts equally on all falling objects, no matter what the mass is. Isaac Newton gave a theoretical proof of this same principle. What Newton did was show that his second law of motion can be equated with his law of universal gravitation. Then the mass on both sides of the equation cancels out, so the acceleration of the body is equal to a constant divided by the square of the distance to the center of the second body. This is such a foundational principle that David Scott, the commander of Apollo 15, felt compelled to prove this principle while he was on the moon.
Shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct in his findings.
Two other key physical concepts important for orbital dynamics are conservation of energy and conservation of momentum. When applied to orbiting bodies, we're interested in the conservation of angular momentum instead of linear momentum. This idea of conservation of angular momentum is probably familiar to anyone who has seen an ice skater spinning in competition. Astronaut Mike Fossum demonstrated conservation of angular momentum himself on the International Space Station.
I have this flashlight rotating. In physics, this angular momentum of an object rotating about some reference point right here in the middle, that's a measure of the extent to which the object will continue to rotate around that point unless it's acted on by an external torque. Now, torque has to do with the ability of a force to rotate an object and how far away from the center that force is applied.
Without the constraints of gravity, he starts spinning with his arms close to his chest at a high rate. Then by extending out his arms, he increases his moment of inertia and the spin rate goes down. And again, bringing his arms back in, his angular rate increases. While linear momentum is expressed as the product of mass and velocity, angular momentum is a product of distribution of mass times angular velocity. The distribution of mass within a solid body about an axis of rotation is called the moment of inertia. So the more precise expression for angular momentum is the product of moment of inertia times the angular velocity. A space station shaped like a ring or donut would have a high moment of inertia, which means it has mass spread out at greater distance from the axis of rotation. As for the conservation of energy, the basic idea is unchanged. The sum of the kinetic and potential energy of an object must be constant. Kinetic energy of a spacecraft is still defined as the product of 1/2 times the mass times the square of the velocity. What's different is potential energy. For objects moving in space, we can no longer rely on Earth's surface as a useful reference plane. And we definitely can no longer assume gravitational acceleration is constant. So we no longer express potential energy as a product of mass times a gravitational constant times height. Instead, potential energy in orbit is defined by the amount of work that it would take to move an object from the center of a planetary body, Earth in this case, through a gravitational field to some orbital position that is a distance r from the center of Earth. The key idea that if we increase the altitude, the orbital radius of the spacecraft, the potential energy also increases. We can think of gravity as a really deep well, a gravity well, and that a spacecraft has to be a very large distance away from Earth before it leaves Earth's gravity well. And we use that as the defined point of zero potential energy. Of course, we never entirely escape the influence of Earth's gravity. It's merely that the gravity of some other object eventually becomes larger. The locations in space where the forces are neutrally balanced between two large bodies are known as Lagrange points. These can be helpful locations for staging a base of operations, since the location of the Lagrangian point is always fixed relative to both of the large bodies. Now, Newton's law of universal gravitation forms the basis for all orbital dynamics and interplanetary flight. Let's assume that a gravitational force from a single body is the only force acting on a spacecraft. That is, there is no atmospheric drag acting on the spacecraft, no thrust, and the gravitational force is from only one body. In this case, we can take Newton's gravitation law and set it equal to Newton's second law. Setting those two laws equal to one another leads to a highly useful and simple algebraic relation that describes the distance of a spacecraft from a planet as a function of the polar angle of the spacecraft within its trajectory. This parametric equation for the so-called two-body problem is conveniently expressed in polar coordinates. The position of the satellite in a plane is described by the radius from the planet to the spacecraft, r, and the angle from the orbit's principal axis to the location of the spacecraft, theta. So the radius from the center of the planet to the spacecraft is a function of the angle theta, together with two constants, a for the semi-major axis and e for the eccentricity of the orbit. More specifically, the radius is inversely related to the cosine of the angle theta. This equation is absolutely stunning in its power. If the eccentricity, e, is less than 1, then the orbit trajectory is elliptical, with a circular orbit as a special case. If the eccentricity is equal to 1, then the trajectory is parabolic. And if the eccentricity is greater than 1, then the trajectory is hyperbolic. The stunning thing about orbital mechanics is that every orbiting spacecraft or planet takes on a trajectory that follows one of these three paths, which from geometry are simply conic sections. And the development of this equation, based on the Newtonian concepts of conservation of momentum and universal gravitation, actually validates Kepler's laws, which stipulated that planetary orbits must be elliptical. Now here's the interesting thing about how the conic sections relate to orbital mechanics. The balance between kinetic energy and potential energy changes, depending on the eccentricity of the trajectory or the type of trajectory a spacecraft is on. First, let's look at the total mechanical energy of the spacecraft. By conservation of energy, total energy is just the sum of the kinetic and potential energy. Let's consider a satellite in an elliptical orbit around Earth, which will be positioned at one of the foci of the ellipse. As the radius of the satellite from the center of the Earth changes throughout the orbit, its potential energy is changing. The point where the satellite passes closest to the Earth is the perigee, and it is at this location where the potential energy is the lowest. So by conservation of energy, the kinetic energy, or the velocity of the satellite, must be highest at the perigee. In contrast, when the satellite is at the farthest point on the trajectory from the Earth, called the apogee, then potential energy is highest. Conversely, kinetic energy and the velocity will be at their lowest. This variation in kinetic energy or velocity around the elliptical trajectory of the orbit directly validates Kepler's second law, which stated that the equal area must be swept in an equal amount of time for any segment of the elliptical orbit. So Kepler's second law was just a geometrical way of stating the conservation of energy for an orbit. The kinetic energy and the potential energy are continually trading off, but the total sum of the energy must be constant. Now let's look at how the properties of the conic section are related to the energy of the orbit. We can take conservation of angular momentum and conservation of energy to obtain an equation that relates the energy of the orbit to the semi-major axis of the orbit, A. That equation said, the total energy of the orbit is equal to the negative of the ratio of the gravitational parameter divided by twice the semi-major axis, A. Remember that the gravitational parameter mu is just the universal gravitational constant times the mass of the body we're orbiting. For various conic sections, the semi-major axis is positive for an ellipse, is infinite for a parabola, and is negative for a hyperbola. When we take these values of A, we find that the total energy for an elliptical or circular orbit is negative. The total energy for a parabolic trajectory is 0, and the total energy for a hyperbolic trajectory is positive. Now, remember, potential energy is always negative by our definition. So if the total energy is negative, as it is for an ellipse, then the kinetic energy is less than the potential energy. And for hyperbolic or parabolic trajectories, the kinetic energy is greater than or equal to the potential energy. This leads us to consider a key question. How much kinetic energy do we need for a particular orbit with a given potential energy or height? Well, the required velocity for a circular orbit is simply the square root of the gravitational parameter divided by the radius of the orbit. So imagine that you want to put an object, such as a baseball, into orbit around the Earth at an altitude just above the Earth's surface. Since the radius of the Earth is 6,400 kilometers, this would require a sustained velocity of 7.9 kilometers per second, or about 17,700 miles per hour. Even the fastest pitcher can only throw about 100 miles per hour. And this mental picture is helpful for understanding the basic idea of an orbit. While the object is in orbit, it is in continuous freefall due to the gravity of Earth. To keep the object in orbit, without coming back to hit Earth's surface, the curvature of Earth's surface must be greater than the curvature of the baseball's orbit. So an object in orbit is always falling towards Earth, but its lateral speed is high enough that the Earth's surface continues to curve away from it. Now, this orbital speed of 7.9 kilometers per second is a helpful parameter for determining the velocity increment required to make it into orbit. If less than that delta V is supplied, then the spacecraft won't make it into orbit. For example, Yuri Gagarin, the first person in space, achieved an orbital trajectory on that first flight on April 12, 1961, where his Vostok 1 spacecraft accelerated to greater than 7.9 kilometers per second for an orbital flight of 1 hour and 48 minutes. By contrast, the first attempt by the US to put a person in space 3 weeks later, on May 5, 1961, was limited to a 15-minute suborbital flight using the Mercury Redstone 3 rocket to take Alan Shepard's Freedom 7 capsule up to a maximum speed of only 2.3 kilometers per second. It wasn't until John Glenn's seminal 4-hour and 55-minute flight on February 20th, 1962, that the U.S. put a person into orbit for the first time.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff. Liftoff. And 34 minutes.
Achieving the necessary velocity with a much more powerful Mercury Atlas 6 rocket. This difference in velocity highlights the huge challenge of achieving Earth orbit. It's an important fact to keep in mind when comparing various space missions. Certain service providers may be able to offer a suborbital flight that makes it into space for a short period of a few minutes, but the bar is much higher for an orbital flight. Now, if we want to raise the bar even higher, let's find the minimum velocity required to leave Earth's orbit. This minimum velocity is called the escape velocity. The only way to fly beyond the confines of Earth orbit is to obtain a trajectory that is either parabolic or hyperbolic. We can find the escape velocity by simply taking our equation for total energy and setting it equal to 0, which is the value of a parabolic trajectory, the threshold between elliptical and hyperbolic trajectories. We find then that the escape velocity is simply the square root of twice the gravitational parameter divided by the distance. For Earth, we note that the escape velocity is 11.2 kilometers per second, or about 25,000 miles per hour. That's 41% higher than the Earth's orbital velocity. So for an elliptical orbit, the potential energy is greater than the kinetic energy. However, for a parabolic trajectory, the kinetic energy is exactly equal to the potential energy. And for a hyperbolic trajectory, the kinetic energy is greater than the potential energy. These relationships give us a strong indication that the spacecraft's velocity at the end of a fuel burn, represented by kinetic energy, will have a dramatic impact on the type of trajectory that is set up. For instance, the New Horizons mission that went to Pluto left Earth with a record-setting velocity exceeding 16 kilometers per second, over 36,000 miles per hour. That's 44% higher than the minimum escape velocity from Earth. Now, what can we do if we want to change the orbit that our spacecraft is in? For example, we might want to take a satellite from an interim low Earth orbit to a high-altitude geostationary orbit, where the satellite speed is the same as the rotational speed of the Earth. How can we minimize the fuel burn required to change the orbital trajectory? Well, these are the questions that were on the mind of a German engineer named Walter Hohmann in 1925. Remarkably, this was more than 30 years before the first man-made satellite was launched into space. So what defines the most efficient orbit change, which is now called the Hohmann transfer? Well, the conditions for the Hohmann transfer assume that the initial and final orbits are in the same plane, that the two orbits have their major axes co-aligned, and that orbital burns can be made as an impulse, that is, instantaneously. Now, an instantaneous burn is not possible in real life, but practically speaking, a typical burn of 2 to 5 minutes is very short compared with a transfer orbit duration of 45 to 315 minutes. For a successful Hohmann transfer from one orbit to another, only 2 impulse burns are required. The first burn will transition the spacecraft from the initial orbit into a transfer orbit, which is the trajectory that will take the spacecraft to the final orbit. Then, a second burn is required at the point of intersection of the transfer orbit to the desired final orbit. The key feature of these 2 orbital burns is that the direction of the applied thrust is tangential with the spacecraft's velocity vector. This means that all of the thrust goes into changing the magnitude of the velocity vector, but not its direction. This is critical for making the Hohmann transfer the most energy-efficient way to get from one orbit to another. Now, the Hohmann transfer can be used to go to a higher altitude orbit or a lower altitude orbit. The direction we go depends on the orientation of the applied thrust. That is, whether the spacecraft is accelerated or decelerated. All that a mission planner has to do is overlay the required transfer orbit on top of the initial and final orbits, ensuring that the transition orbit is tangent to the other 2 at the points where they intersect. Then, based on the energy characteristics of each of the 3 orbits, the velocity change, known as the delta V, can be found for each transfer. And once the delta V for each burn is known, then the required amount of fuel mass can be determined from the rocket equation that we studied in the previous lecture. And keep in mind, all we're doing with the Hohmann transfer is changing the overall energy of the trajectory, with the minimum fuel burn required. So, for example, let's consider the burns and transfer orbit required to move a communications satellite from a low-altitude parking orbit of 6,570 kilometers from Earth's center, an altitude above Earth of only 192 kilometers, up to a much higher geosynchronous orbit of 42,164 kilometers from Earth's center. At the lower initial circular orbit, the velocity of the spacecraft will be 7.79 kilometers per second. The first burn must have a velocity increment of 2.45 kilometers per second, bringing the velocity up to 10.246 kilometers per second at the perigee of the transfer orbit. Then, as the satellite follows the elliptical transfer orbit trajectory, it will slow down to 1.6 kilometers per second at the apogee of the transfer orbit, where the second rocket burn will add 1.48 kilometers per second to bring the satellite up to a geostationary velocity of 3.08 kilometers per second. Now, it may be surprising to note that the final velocity of 3.08 kilometers per second is lower than the initial velocity of 7.79 kilometers per second, despite adding a delta V of 3.94 kilometers per second. What happened to that added velocity? Remember, the new orbit is at a much higher altitude with much higher potential energy. So the total energy of the new orbit is much higher, even if the kinetic energy is lower. Okay, now what do we do when we need to rendezvous with another spacecraft that is at a different location in orbit? This is a big challenge that was tackled by the Gemini program in the mid-1960s, as the United States was preparing for the Apollo missions to the moon that followed. Learning how to successfully rendezvous in space was critical, because the basic premise of the lunar mission depended on it. Let's take a look at Apollo 11 for a moment, and then we'll return to the Gemini program's efforts to solve the challenging problems that made Apollo possible. The Apollo 11 lunar mission began with launch of the huge 3-stage Saturn V rocket, which placed the spacecraft into a parking orbit around Earth at 180 kilometers. After orbiting Earth for 1.5 revolutions, a 5-minute and 48-second long burn was made to transition from Earth orbit to lunar insertion trajectory. Apollo 11 was the first of the Apollo missions to put astronauts on the moon. At the beginning of the outbound leg of this lunar transition, the command module needed to separate from the booster, turn around, and dock with the lunar module. This lunar module-command module pair then had to travel along the lunar insertion trajectory for nearly 3 days and perform a burn to enter lunar orbit. 2 members of the 3-person crew had to transition into the lunar module, leaving 1 person behind to man the command module in orbit around the moon. The lunar module would then descend to the lunar surface for the scientific mission. Then the ascent stage of the lunar module had to blast off from the lunar module, ascending on a trajectory designed to reach lunar orbit.
1,000 feet high.
And here's the tricky part. The ascent stage needed to successfully rendezvous with the command module in lunar orbit. If this was not successful, the astronauts in the ascent module would miss their ride home and be stuck in space. Now, a successful rendezvous of 2 capsules is all about timing. The best analogy for this is actually a Hail Mary pass in football, where the quarterback lofts the football high in the air for a long pass down the field. Meanwhile, the receiver is sprinting down the field, and the goal is for the receiver's path to intercept the football's path at exactly the right time in the end zone for a touchdown. It's the quarterback's job to estimate the right time to throw the football while the receiver is sprinting down the field. The key factors here are the speed of the receiver, the speed at which the football is thrown, the rendezvous location, and the delay time between the snap of the football when the receiver heads down the field and when the ball is thrown. The same factors are true for 2 spacecraft that must rendezvous. For the lunar module on the surface of the moon, the timing of the launch has to be just right, such that the velocity of the ascent module makes it up to the orbit of the command module with an arrival time for the precise moment when the command module would pass by. This is the exact challenge that the Gemini program had to work out. For example, on the Gemini 8 mission, Neil Armstrong and Dave Scott were the astronauts tasked with testing out rendezvous procedures with an unmanned Agena target vehicle that had been previously placed into orbit. After initial launch of the Gemini 8 into orbit, the astronauts had to do only a few short burns of thrusters on the orbit attitude and maneuvering system to correct their orbit and approach the Agena vehicle. The first burn was a short 5-second burn that lowered their apogee ever so slightly. Then their second brief burn added just 15 meters per second to their speed, which raised both their apogee and perigee. Finally, one more short burn added just 0.79 meters per second to their orbital speed. As the 2 vehicles closed in on one another, the astronauts did a few short burns to bring the relative speed between the 2 vehicles down to 0. This afforded the astronauts the opportunity to inspect the Agena vehicle and prepare for docking. Finally, they started to proceed at a snail's pace of 8 centimeters per second until they successfully mated with the Agena and the docking latches engaged. They had just accomplished a huge feat by becoming the first to successfully dock in space. However, the euphoria of that success didn't last for long. Shortly after docking, the spacecraft pair sped along their orbit, about to enter a period of radio blackout where no communications with ground control were possible. The Agena vehicle, with a full load of propellant on board, began executing some pre-programmed maneuvers to reorient the spacecraft pair. However, as it began these maneuvers, the astronauts recognized that they were starting to spin out of control. Thinking that the problem was with the Agena vehicle, they quickly undocked in an attempt to stabilize the situation and regroup. However, the problem was with their own spacecraft. Now that they had undocked from Agena, their moment of inertia was much lower, and the spin rate actually increased, where they were tumbling end over end. By the time they came back within radio contact, the Gemini 8 capsule was spinning at a rate of 360 degrees per second, fast enough to dangerously threaten the astronauts with vertigo or even blackout. Armstrong had the presence of mind to shut down the orbit attitude and maneuvering system and instead used thrusters on the separate re-entry control system to stabilize Gemini 8. Taking stock of the situation, they troubleshooted until they diagnosed that one of the thrusters on their orbit attitude and maneuvering system had been stuck on, which was later determined to be due to an electrical system short. At this point in their mission, they had burned almost 75% of the propellant in the re-entry control system, which was critical for safely returning to Earth. Armstrong and Scott then made an emergency return to Earth and a safe landing. And as we know, each of the two astronauts would later walk on the Moon, in Apollo 11 and Apollo 15, just a few years later.
That's one small step for man, one giant leap for mankind.
So the Gemini program, through a series of tests, ultimately demonstrated that rendezvous and docking maneuvers could be done safely and effectively. This is one of the critical risk reduction steps that enabled NASA to mount a successful Moon mission. Now there's one more interesting aspect of an orbital rendezvous that we should consider. How can one spacecraft catch up to rendezvous with another one that is in the exact same orbit? It can't accelerate along the same path to catch up. The velocity increment would take it to a new orbit. Let's consider two spacecraft in the exact same circular orbit. The spacecraft playing catch-up would have to apply thrust for a velocity decrement in order to enter an elliptical orbit with a shorter period than that of the original circular orbit. The period of the new orbit, of course, should be timed such that the spacecraft will re-enter the original circular orbit at the precise time when the other vehicle passes by. So the spacecraft playing catch-up can slow down and take a shortcut in order to successfully rendezvous. This also illustrates a more general principle distinctive to space travel. Losing speed requires no less effort than gaining speed. Now let's discuss one final aspect of the Apollo mission trajectory that ended up being critical for the successful return of the ill-fated Apollo 13 flight. All of the analysis that we have been considering so far is for a two-body problem, where only the spacecraft and the body that is orbiting are accounted for in the analysis. However, lunar missions are inherently a three-body problem, where the gravitational field of both Earth and Moon have a significant impact on the trajectory of a spacecraft. In fact, there is a way to make use of both gravitational fields to obtain what is known as the free return trajectory, which follows a figure-8 pattern around the Earth and the Moon. The main idea of the free return is to rely on the gravitational field of the Earth-Moon system to bring the spacecraft back to Earth without additional thrust being required after the initial burn to move the spacecraft from Earth orbit into the lunar insertion trajectory. The spacecraft would aim for the far side of the Moon, whose gravitational field would slingshot the spacecraft back towards Earth. In June 1963, Arthur Schwaniger wrote, somewhat presciently, that a free return trajectory may be used so that if unforeseen difficulties arise, which would make landing undesirable or impossible, the astronauts will return safely to Earth. Of course, this is exactly the problem that occurred in April 1970, 7 years later, when the Apollo 13 spacecraft suffered an explosion in the service module while the spacecraft was outbound on the lunar insertion trajectory. Because Apollo mission planners had already included a contingency for returning by a free return trajectory, they had the option, which was deemed to be the safest, to use that free return trajectory rather than doing an extended burn to directly return home. The free return trajectory took extra time, but it did set up Apollo 13 for the appropriate return trajectory to Earth. For similar reasons, a free return trajectory is also being considered in the planning for possible missions to Mars. If some catastrophic event is encountered while en route, the astronauts will have a ride back home while using very little extra fuel. This is the power of orbital mechanics, that a spacecraft can work within the confines of gravitational fields to its advantage.